Have you ever asked yourself how prime numbers really come into being? Not how to find them. Everyone learns the sieve in school. You cross out the multiples of 2, then the multiples of 3, then 5, and what is left over are the primes. But that procedure tells you nothing about why the primes sit where they sit. It is just a filter. The question I want to ask in this video is different. Is there a shape, a geometry, a body that the prime numbers naturally live inside? The answer, it turns out, is yes. And the body has 8 corners, 24 edges, 32 faces, and 16 cells. It lives in 4 dimensions. And when you look at it from the right angle, the prime numbers fall into the points of a Star of David. Let me show you how this came together. It started with a matchstick game. The rules are almost childish. Place small triangles on a board, mirror them at the number 2, build outwards step by step. I will not go through the rules here. The point is that the game does not know about prime numbers. It only knows about triangles and mirrors. And yet, when you play it long enough, the prime numbers appear on their own. They show up at exactly the positions where the geometry permits them. The game produces the primes without ever being told what a prime is. That was the first surprise. The second surprise was that the matchstick board is flat. It is 2-dimensional, and the prime numbers seem to want more room than that.
Here is what I mean. Take any prime number larger than 5, divide it by 30, look at the remainder. School mathematics calls this a residue. A residue is just the rest after division. For example, the prime 37 divided by 30 leaves a remainder of 7. The prime 41 leaves a remainder of 11. If you do this for every prime above 5, you find something striking. The remainder is always one of exactly 8 numbers: 1, 7, 11, 13, 17, 19, 23, 29. Always, without exception, forever. Other remainders are forbidden. A prime cannot leave the remainder 15 because 3 divides 15. It cannot leave the remainder 25 because 5 does. Every even remainder is forbidden because 2 does. What is left is this clean, finite, 8-element set. Now look at the symmetry of those 8 numbers. 1 and 29 add up to 30. 7 and 23 add up to 30. 11 and 19 add up to 30. 13 and 17 add up to 30. 4 mirror pairs, 8 numbers. A reflection symmetry around the value 15, which sits exactly halfway between 0 and 30. That pattern is too clean to ignore. 8 points, 4 reflection axes, every pair the same distance from the center. What kind of body has this structure? A cube has 8 corners, but the symmetry is wrong. The cube reflects through its faces, not through opposite corners. An octahedron has 6 corners, wrong number. In 3-dimensional space, no familiar body fits. But in 4 dimensions, exactly one body fits, and it fits perfectly. Mathematicians call it the cross-polytope in 4 dimensions, or the 16 cell. It is the 4-dimensional analog of the octahedron. From now on, I will call it the Prime Hyperoctahedron because it is the natural carrier of the 8 coprime residues modulo 30. The construction is simple. Take the 4 coordinate axes in 4-dimensional space. On each axis, put a point at +1 and another at -1. That gives you 8 points. 4 mirror axes through opposite pairs. Every point at the same distance from the center. There is no choice. This body has structure at every dimension. It has 8 corners. It has 24 edges connecting non-opposite corners. It has 32 triangular faces. It has 16 tetrahedral cells. And here is the second clean fact. If you label each edge by the sum of the 2 corner residues modulo 30, the 24 edges hit exactly the 14 even residues from 2 to 28. The number 30 itself never appears because 30 would correspond to the mirror axis, which has 0 length. If you label each face by the sum of 3 corner residues, the 32 faces hit the 14 odd residues from 1 to 29, except for 15. 15 is the center of the symmetry, and the geometry refuses to express it as a face. If you label each tetrahedral cell by the sum of 4 corner residues, the 16 cells hit the 15 even residues from 2 to 30. Now 30 is allowed because 4 corners can wrap around once. 4 pillars. Each one points to the same axis of symmetry. None of this was put in by hand. It comes out by counting.
Now for the final step. A 4-dimensional body cannot be drawn on paper, but it can be projected. Imagine shining a light through it and catching the shadow on a flat surface. The question is, which flat surface produces the most beautiful shadow? Among the 32 faces of the Prime Hyperoctahedron, 3 faces are special. Their 3 corners are equally spaced, the side lengths are equal, and the residue sum is 1 modulo 30. One of these special faces has the corners 7, 11, 13, 3 consecutive primes, an equilateral triangle. Project the whole body onto that triangle. What you get is this. 3 corners land on the triangle itself, 7, 11, 13. The opposite 3 corners, 17, 19, 23, land on a second equilateral triangle, same size but rotated 180 degrees. The 2 remaining corners, 1 and 29, land at the center on top of each other. 2 interlocking equilateral triangles, a Star of David, with 2 faint points hidden at the heart. This is the picture. It is the unique shadow that the 4-dimensional carrier of the prime residues casts onto its own most symmetric face. No mysticism, no tradition, just geometry. I want to be honest about what this is not. It is not a proof of the Riemann hypothesis. It is not a new sieve for finding primes. It is not a complete theory of how primes are distributed. What it is an answer to the question I started with. The prime numbers above 5 must live in one of 8 residue classes modulo 30. Those 8 classes form a unique 4-dimensional body. That body, projected the right way, gives a Star of David. So when somebody asks where the prime numbers come from, here is one answer. Here is the geometry that produces your primes.